Okay, so far we have a couple different ways to come up with the sine and cosine and tangent of a particular angle in a particular quadrant. So the first way that we looked at was the geometric model, which is the way that you guys learned it in Algebra 2, at least that's probably how you started. And then we looked at trig identities, which was uncovering, using the Pythagorean theorem, coming up with the identities or coming up with different manipulations that we know are also true. So today, the last section in this chapter is talking about the unit circle. Now, we're not going to dive too much into the unit circle. We're dealing with this really in chapter 2 and beyond about like specific angles really, but we're going to talk a little bit about the unit circle and really kind of uncover what we talked about today, or yesterday, which was talking about the sines and how at those quadrantal angles our geometric model falls apart. So we need another way to deal with that, and really it comes with the unit circle. So the unit circle is really just a model that represents our trig function. So it's more of an algebraic way, more like our trig identities. But if we have a circle that represents all the possible values that are a specific distance away from our center, the center of our circle is going to be here at the origin, 0, 0, and we are representing all the set of values that are at a distance 1 away from that. So our radius is 1 on our unit circle. Everywhere that we draw in our radius, we end up getting that value of 1, and then we can kind of create this into a reference triangle. Now, this is the actual true definition of sine and cosine, rather than looking at a geometric perspective. It's really on our unit circle, it corresponds with these particular values. So if I actually draw in a terminal point, so on my unit circle, I'm going to say that I'm at that point, which really is kind of like a terminal side. I can create a reference triangle, just like we've been doing. This is our theta, again, between the reference or the terminal side and the x-axis. So our x and y coordinates, and our unit circle, this is 1. And this simplifies things a lot more because now when we actually look at our sine and our cosine, our sine value is going to be y over 1, which is just going to be y. So on the unit circle, our x and y coordinates correspond with the cosine and the sine values. So our x value really is the cosine of theta, and the y is the sine of theta. We've been grouping them together for a while, saying that really our cosine depends on our x value and our y depends on our sine value, and it changes the sign of those things, and that's why our radius was always 1, or our value was always 1. It's because on the unit circle it's a set distance. And again, this is really important. The unit circle is really important when you dive further into trigonometry, where you can't explain everything geometrically. And it also simplifies things a little bit that we can represent any point on our circle as some x and y coordinate, which is also then our cosine and our sine value on the unit circle. And again, that simplifies things because we don't have to draw a reference triangle every time. We know that it represents, or that there's a reference triangle that we could draw, but in general, we can just look at our sine and cosine and look at the ratios of those things. We only care about then the x and y coordinates rather than our value as we're looking for it. So we can still, since we can draw a reference triangle, we can still use a geometric model, and sometimes it's easier. We just have to make sure that the proper reference triangle is drawn. And again, sometimes it's a lot easier to do that in that case. Like for this one, for example, if we are looking at this sine value and we know we're in quadrant 1 and we're trying to find the cosine, in our geometric model, we would draw our reference triangle in quadrant 1. This would be our angle. Our sine would be our opposite over our hypotenuse. And then we would solve for my x-coordinate, which you know would be 4. Since it's a 3, 4, 5 triangle, and we would say that our cosine of theta is 4 over 5, if our sine of theta is 3 over 5. Now that one's like really simple, and Maybe the unit circle method is not as good because the geometric model makes sense, but I promise you that the unit circle model will end up using that more and more because it's really, really useful when we look at specific triangles that are drawn, like our special right triangles that are drawn. It's really important to know our x and y coordinates because it corresponds with our sine and our cosine value, and it makes our life a lot easier at that moment. But for now, like if you want to stick with the geometric model, that's fine. I'm not going to take off points for it. I might say, you know, on some practice assignment that I want you to do it both ways or something. That's fine, but on the test, it won't specify. You could use the geometric model if you want. You just have to make sure, again, that you are in the right quadrant. So if I was going to use this with the unit circle, I'm still going to draw a triangle, but it's not going to be like my opposite and my hypotenuse anymore. I'm going to represent my y-coordinate, since sine of theta is 3 over 5. And I know that in my unit circle, this is really my y-coordinate. I'm going to label this as 3 over 5. And my hypotenuse is 1 on the unit circle. And this is really what we're looking for, this x value. Now again, x is cosine, so when we solve for our x value, really what we're solving for is our cosine value. So if I were going to, put my theta. If I was going to actually solve this, I could use Pythagorean theorem. So similar, same kind of principles that we've been dealing with. So I'd have our x squared, which is cosine squared, plus my other leg that I have, 3 over 5, quantity squared equals 1 squared. And then when I solve this, let's see, I'll get 9 over 25 equals 1. I'll subtract 9 over 25 from both sides, so 25 over 25 minus 9 over 25 is going to be 16 over 25. And then I take the square root. Don't forget that we have plus or minus. We are in quadrant 1, so we're going to take the positive version of this. And we'll get square root of 16 is 4 and square root of 25 is 5. So we still get the same answer. Obviously, this way was way less, like a lot less work, and it's completely fine if you still do this way. And it probably makes more sense right now to do it this way than to use the unit circle method. I just wanted to show you the difference in the triangles that we're drawing. So in our geometric model, we are using the fact that this is like opposite and hypotenuse, but in our unit circle model, we're saying that our sine value is the y-coordinate. So our legs are always going to be represented as some sort of fraction that's under 1. Remember, the range of sine and cosine is between -1 and 1. So these will always be some sort of fractions, and our hypotenuse of our triangle is always going to be 1. But either way will work. We're going to lean again towards the unit circle model later on when we do lots of other trig stuff, because it comes up a lot more and it's more important to use the unit circle model, and it will make more sense as we go through, like even when we go through graphing, to actually look at sine and cosine and tangent in that way. But for now, you can use either. And again, I said at the beginning that we really need our unit circle model to kind of explain some of the ways that our geometric model failed us when we talked about our range between -1 and 1 for sine and cosine, and that's really what happens at our quadrantal angles when some stuff gets kind of messed up. So our quadrantal angles are the angles whose terminal side ends on an axis, so where we can't actually draw a triangle, so it can't actually make sense to use a geometric model. So that means that we can actually use our unit circle model. And knowing the unit circle and that model, that you have a distance that's a distance of 1 away from that center point of 0, 0, and explaining that our y-coordinate is really our sine value and our x-coordinate is really our cosine value, makes finding the trig values for those quadrantal angles really, really easy. So I'm going to draw out a little picture so we can kind of reference this while we're looking at it. So here's our unit circle. And again, we're specifically looking at these quadrantal angles. So if this is our terminal side here, we're starting at angle 0, and then this will be a 90-degree angle, 180, 270, and then one rotation gives us back to 360. So again, in our unit circle method model, our x value is really our cosine, and our y value is our sine. So at any point, again, on our unit circle, we can come up with an x and y coordinate, and that would represent our sine and our cosine values. So that means at this coordinate point, which is at 0 and 360 degrees, I can represent that as 1, 0. It's a distance of 1 away. At our 90-degree angle, I can represent that as 0, 1, because I'm 0 on my x-axis and 1 on my y. At 180 degrees, I'm at -1, 0. And at 270 degrees, I'm at 0, -1. So again, it's really helpful to use this model to represent these specific values. Now we have a method of explaining why we can get sine is equal to 1, even though we can't actually draw that triangle that would be in this spot. This would just be like a single line. So this explains and helps us come up with that range. So at 0 degrees, our sine value is really our y value. So at 0 degrees, my y value is 0. So my sine is 0. At 90 degrees, my y value is 1. So my sine of 90 would be 1. At 180 degrees, my sine value is 0, because my y value is 0. And at 270 degrees, my y value is -1, so my sine value is also -1. And then at 360 degrees, that's really coterminal with 0. So you can see that we're going in this pattern. And between these values, so I'm going from 0 to 1, my sine value is going to be increasing, because I'm getting closer and closer to 1. And then it decreases because my y coordinate's decreasing, and I'm going closer to 0. And then it's getting bigger in the negative direction, because my y value again is getting deeper into the negatives. And then it's going back to 0, so it's going to get less, less negative as I go up to that 0. And so you can see it's kind of this cyclical pattern where we're going to keep going in that same direction. As I go and come up with more terminal angles, I'll be oscillating between 0, 1, and -1. And all those values that are in between, I'm hitting all of those sections. So same thing with cosine. If I was looking at cosine of 0 degrees, I would be looking at my x value, so that would be at 1. At 90 degrees, my cosine is 0. At 180 degrees, my cosine is my x value at -1. And at 270 degrees, my cosine again is my x value, which is at 0. And then back at 360, I'm back at 1. So again, same idea. I'm oscillating again between 0 and -1. I'm really looking at how my x value behaves along my unit circle. So I'm starting out here at 1, and then I'm getting closer and closer to 0 on my x-axis. I'm just lining up with my y-axis here, so I'm getting closer and closer to 0. And then I'm getting more negative, going to -1, getting back closer and closer to my y-axis, which gives me an x-coordinate of 0, and then again back to 1. So again, I'm oscillating between those. Remember, tangent is defined as our one of our quotient identities, was that it's sine over cosine, and that makes for finding our tangent values at each of these quadrantal angles kind of easy. So if I arrange it in this way and I look at tangent being 0 sine over cosine, that would be 0 over 1, which means our tangent, being the ratio of those two values, is going to be 0 at that point. At 90 degrees, it'd be 1 over 0, which gives, something that's undefined. So this doesn't actually exist, which means that 90 degrees is not something I can plug into my function. This would be a domain restriction, and later on we'll talk about the domain specifically of tangent. We'll talk about all the domains for all the trig functions, specifically tangent and cosecant and secant. We kind of talked about those when we talked about the range, how there are values that you can't actually plug in and get corresponding y coordinates or y values for. And 90 degrees is one of them for tangent, because that's when our fundamental problem of having a denominator equal to 0, where cosine is 0 will give undefined values for my tangent. So for 180 degrees, if I look at the ratio of my sine over my cosine, I'm 0 over -1, which is 0. Again, at 270, I have an issue because my ratio of -1 and 0 is going to give something that's undefined. And then back at 360, it's going to be the same as 0 because they are coterminal angles. This table, not specifically the table, but all these values at these particular quadrantal angles need to be known for your test on Friday. Once you know that it's represented by the unit circle, it's really easy to come up with the quadrantal angles. So if I said, what's the tangent at 90 degrees, you could use our unit circle method to actually figure that out rather than just memorizing it. And that's what I would recommend. Like if you have an understanding of what this is, then you can, you don't have to memorize. If you understand how to get all these things by using our quadrantal angle unit circle idea, then that's something that you don't have to, again, necessarily memorize. So what we're going to do for the next couple minutes is just look at these evaluations at these specific angles. So we're going to use our unit circle and our quadrantal angles to get there. So at 270 degrees, so we have 3 times the sine of 270. At 270, we're here. We're at -1 or 0, -1. Sine is -1 since it's the y value. So we're looking at 3 times -1. For cosine of 0, we have 2 times cosine of 0 at 0 degrees. We're over here. We're at 1, 0. Cosine is our x value, so it's going to be 2 times 1. And then at 180 degrees, we're looking at our ratio of sine over cosine, so that's 0 over -1, which gives 0. So all in all, I have -3 plus 2 minus 0, so that will give me a value of -1. For our next one, same kind of idea. At 180 degrees, I'm this way on my unit circle. I'm looking at my x value because I'm dealing with cosine, so it's at -1. Cosecant, remember, is 1 over sine, so really we're evaluating 1 over sine of 270 degrees. So we have 3 times 1 over our sine at 270 is my y value down here, so that's 1 over -1. And same thing for secant, that's cosine, so we're looking at 1 over cosine squared of 180 degrees. So 1 over cosine of 180 degrees squared, 180 degrees is halfway around my unit circle, looking at my x value, which is -1. So we'll simplify, we get -2, -1 over -1 is going to be -1 times 3, so -3, and then -1 squared is going to be +1, 1 over that's going to be +1. So I get -5 plus 1, which is -4. Again, I know that the geometric model doesn't really help, or sorry, the unit circle model doesn't help with some things like this, like coming up with our sine and cosine for, something that's already given and it's a more geometric way. But what it does do is it helps us explain those values, those quadrantal angles, and it'll be really, really, really useful to us once we get into chapter 2 and beyond.